Hey everyone, and welcome to another deep dive. This time, we're going to tackle some serious math.
Serious math, that's right.
Yeah, we're talking 20th century math, like the big ideas that still matter today.
Exactly. Stuff that still shapes how mathematicians think.
I know. Math history can be a bit dry sometimes,
Right.
but trust me on this one, folks. This is different. We're going for like the core insights.
Yeah, the insight's not just a bunch of dates and names.
Exactly. Think of it as a high-level view of the landscape.
Yeah,
You know,
exactly.
perfect for math students who want the big picture.
Absolutely.
So our guide for this adventure is a lecture by Sir Michael Atiyah.
Oh, a legend.
Yeah, a total giant in the field. He gave this amazing talk where he looked back at the key themes of the whole century.
Wow.
And that's what we're going to unpack today.
Sounds good.
Buckle up.
So one of the first things Atiyah talks about is this shift from the local to the global.
Local to global. Okay.
Yeah, and it's really this like an underlying current that runs through so much of 20th century math. You see it in almost every field.
So instead of just like obsessing over specific points or, one equation at a time,
Right. Yeah.
it became about understanding these bigger structures,
Yeah.
like patterns that connect everything.
Exactly.
Like that makes sense, right? Because even in basic calculus, you learn about like how the derivative at one point,
Right.
it tells you about the slope, but doesn't tell you the whole shape of the curve.
Exactly, and that's just the beginning. Think about something like the Gauss-Bonnet theorem.
Gauss-Bonnet.
It connects the curvature of a surface locally, like at each point, to its overall global shape. It might sound kind of abstract, but it's a huge deal.
It is.
Oh, yeah. It means we can study these crazy complex shapes by just analyzing their teeny tiny parts.
Whoa, that's mind-blowing.
It is. And it's not just geometry either. You see this local to global idea in other areas, too.
Oh, yeah. Like what?
Like, well, think about the Riemann-Roch theorem.
Okay, Riemann-Roch. That's complex analysis, right?
You got it. It connects the number of holes in a complex curve to the behavior of certain functions on that curve. And it's not just a theoretical thing either. It's got real-world applications.
No way.
Yeah, like in algebraic geometry, even string theory.
So this local to global thing, it's like a secret code. It unlocks all these different areas of math, right?
It's a great way to think about it. And remember, it wasn't just about math, this shift. It reflects a broader change in how we understand the world, from looking at things in isolation to seeing how everything's connected.
Oh, that's deep.
It is, isn't it?
Okay, so big shifty perspective, check. But Atiyah, he didn't stop there, did he?
Oh, no, he didn't. He goes on to talk about another major development, the realization that multiplication isn't always commutative.
Wait, what? You mean like A times B equals B times A?
Right, exactly. For
Yeah.
centuries, everyone just took that for granted.
It's like the most basic rule of multiplication.
It is. But then, mathematicians started exploring these more abstract systems,
Like what?
quaternions, matrices, and suddenly, order mattered. It was revolutionary.
I can imagine. Like that must blown some minds back then.
Oh, it definitely did.
So how did mathematicians even begin to wrap their heads around this non-commutative world?
Well, it led to a whole explosion of new math. Quaternions, which were like mind-boggling at the time, they're now essential in things like computer graphics, robotics, because they represent 3D rotations in this really elegant way.
Wow.
And matrices, well, they're everywhere. Non-commutative multiplication and all.
So breaking the rules, it actually pushed math forward in a good way.
Exactly. And it wasn't just pure math either. Even physics got in on the action.
Oh, yeah. How so?
Well, the Heisenberg uncertainty principle in quantum mechanics, that's all about non-commuting operators. And then there are the Yang-Mills equations. Those govern the fundamental forces of the universe.
Okay, so the universe itself is playing by these non-commutative rules.
Wow. It is. And, for any students listening, understanding matrices and all their quirks, that's like a key to a whole new level of understanding, both in math and physics.
Got it. Matrices, they're the gateway drug to the good stuff.
That's one way to put it.
Okay, so 20th century math, it's already sounding pretty wild. And we're just getting started. What else did Atiyah have in store for us?
Well, he tackles a real classic, the whole geometry versus algebra debate.
Ooh, that's a juicy one.
It is, but it's not about one side winning. It's about two fundamentally different ways of approaching problems.
So is it like choosing between visual intuition, like seeing the solution, versus hardcore logic and
You
symbols.
could say that. Geometry, it's about space, shapes, the visual, those aha moments when you see a proof and it all clicks, like tapping into how our brains are wired.
That makes sense. I'm definitely a visual learner, so geometry always felt like more natural to me.
What about algebra then? Well, think about it this way. Algebra, it's about time, about processes, algorithms. Like, it's the language of computers, executing instructions step by step.
Okay. I can kind of see that.
And Atiyah makes this interesting point about algebra. He compares it to this Faustian bargain.
A Faustian bargain. Interesting.
Yeah, like you gain incredible power, but there's a cost. You risk losing sight of the meaning behind all the symbols.
Oh, it's deep.
It is. So algebra, it's speed, efficiency, but maybe you lose some depth of understanding compared to geometry.
So it's a trade-off then.
Exactly. And as a student, you might find yourself gravitating towards one or the other. But the real masters, they're fluent in both languages.
I see, yeah. Being able to switch back and forth between those ways of thinking, that's where the magic happens.
Absolutely. Seeing a problem from both the geometric and the algebraic perspective, that's incredibly powerful.
I can imagine. All right, so we've got local to global, non-commutative craziness, geometry versus algebra. This is a lot to take in. Where do we go from here?
It's easy to get kind of, caught up in these big ideas. But sometimes the most exciting stuff in math comes from those niche areas, those problems that have been bugging people for ages.
Oh, I like where this is going. You're talking about those like mathematical mysteries. We have the ones that seem simple at first, but then...
Exactly, like deceptively simple.
Yeah, and then they turn out to be like incredibly deep and complex.
Yeah, like rabbit holes that go forever.
Okay, so give me an example. What's one of these mysteries?
Okay, well, how about the classification of finite simple groups?
Finite simple groups.
Yeah, it's this massive achievement in algebra. Took decades to solve, tons of mathematicians involved.
I got to be honest, group theory, it's still a bit of a mystery to me.
Fair enough. Think of groups as like ways to describe symmetry.
Symmetry?
And a simple group, well, it's like a basic building block of symmetry. It can't be broken down any further.
So like the prime numbers of the symmetry world.
Exactly. And what's amazing is that most of these groups, they fall into these well-known families.
Oh, okay.
But then there are these oddballs.
Oddballs.
Yeah, like these sporadic groups. They don't fit the pattern.
So there are like these rogue symmetry groups out there just doing their own thing.
Pretty much. And the biggest of these, a real monster, it's called the monster group.
The monster group, that's awesome. How big are we talking?
Well, it's got over 808 non-million elements.
Okay, that's just a kidding.
It's a number so big it's hard to even fathom.
I believe it.
Yeah.
So besides its size, what makes this monster so special?
Well, it's this crazy complex thing, right? But it has these unexpected connections to other areas of math.
Really?
Oh, yeah. It pops up in the study of elliptic modular functions and even has links to string theory.
So even in this really specific part of algebra, we see those connections that Atiyah was talking about, bridging different fields of math.
It's like the monster group is this mathematical Rosetta Stone. It hints at some deeper relationship we don't fully understand.
I love that analogy.
And this interplay between fields, it happens all the time in 20th century math. Remember we talked about homology, K-theory, tools that came from different areas but ended up being super useful everywhere.
Yeah, like mathematical Swiss Army knives.
Exactly. And then there's the whole impact of physics, which, didn't just inspire mathematicians, but it gave them concrete tools, reshaped how we think about geometry, topology.
So it's like math is this giant web, and the more we learn, the more we see these unexpected connections between things.
It's all connected, and those connections, that's what makes math so cool. It's not just solving equations. It's about understanding the deep structure of the universe, like pushing the limits of what we can know.
Okay, I'm feeling inspired. But you also mentioned Atiyah talking about nonlinearity. What do you mean by that?
So for a long time, math focused on linear stuff or nearly linear. Think, Euclidean geometry, straight lines, simple shapes, or calculus where we use tangent lines to approximate curves.
Right, those linear approximations, always a pain.
They are. But the real world, it's rarely that neat and tidy,
Yeah, tell me about it. Things are messy, complicated.
Exactly. Systems are complex, interactions are all tangled up. And that's where nonlinearity comes in. It's about tackling that messiness head on.
So like embracing the chaos.
In a way, yeah. And it opened up all these new possibilities in math, phenomena that you just couldn't explain with the old linear models.
Okay, I'm intrigued. Give me some examples of this nonlinear world.
All right, so there are these things called solitons.
Solvent again.
They're these stable, solitary waves. They show up in all sorts of systems like water waves, fiber optics, even DNA.
No way, really.
Yep, completely unexpected discovery, but it shows how this amazing order can emerge from nonlinearity.
So even in chaos, there can be patterns.
Exactly. And of course, there's chaos theory itself.
Oh yeah, chaos theory, the butterfly effect, right?
That's the one. It highlights how sensitive chaotic systems are to initial conditions. Like, a tiny change at the beginning can lead to totally different outcomes down the line.
It's kind of scary when you think about it.
It is. And for mathematicians, embracing nonlinearity meant accepting the limits of predictability. It wasn't easy, but it was also incredibly freeing.
Freeing how?
It opened up new ways of thinking, new tools for understanding this complex world we live in. And this shift wasn't just in math either. It happened across all of science. Biology, ecology, economics, they all started to realize that things are way more interconnected than we thought.
The whole is greater than the sum of its parts, right?
Exactly. And this idea had a huge impact on the relationship between math and physics. Remember those Yang-Mills equations?
Yeah, the ones that govern fundamental forces, right?
Those are fundamentally nonlinear. And that nonlinearity comes directly from the noncommutative nature of matrices.
Oh, wow. So it all comes full circle. Non-commutativity, non-linearity. They're like two sides of the same coin.
They are. And this brings us to another key theme of 20th century math. The rise of Lie groups.
Lie groups, right.
Yeah.
I think we need a deeper dive on those. What exactly are they, and why are they so important?
Well, think of them as groups that have this smooth, continuous structure, like a curve or a surface.
Okay, so they capture that idea of smooth change, like a continuous transformation.
You got it. Rotations, translations, scaling, those are all examples of Lie groups.
Got it. But why are they so important?
Well, they're fundamental to geometry, topology, even algebra. They give us a powerful way to understand symmetry, which is a key concept in so many theories, both in math and physics.
Okay, so give me some specifics. How do Lie groups actually show up in different areas?
Well, in geometry, they're essential for understanding curved spaces,
Right.
like the space-time of Einstein's general relativity.
Wow, so they help us describe the fabric of the universe. That's pretty cool.
It is. And in topology, they're used to study these things called topological invariants. Those are properties of shapes that don't change even when you, like, stretch or twist them.
So they help us distinguish between different types of shapes, even if those shapes are all deformed.
Exactly. And in algebra, Lie groups are closely tied to Lie algebras, which are these non-commutative structures that capture the infinitesimal behavior of Lie groups.
It's like zooming in on a Lie group at a single point and seeing its algebraic essence, right?
That's a great way to put it.
Okay, so Lie groups, they connect geometry, topology, algebra. They help us understand symmetry and continuous change. Sounds like they're a pretty big deal.
They are, and they just kept getting more and more important throughout the 20th century.
So Atiyah was right to see them as this unifying force in mathematics.
Absolutely. And their influence goes beyond pure math, too. Remember all that talk about symmetry in physics? Well, Lie groups are like the mathematical language of symmetry. They play a key role in everything from quantum mechanics to string theory.
So again, we see this beautiful convergence of math and physics.
It's amazing, right? And this convergence, it got even deeper in the late 20th century. Physicists started using Lie groups to study these crazy infinite dimensional spaces, like in quantum field theory.
So Lie groups, which started out as a tool for studying finite dimensional geometry, they ended up being crucial for understanding some of the most advanced theories in physics.
It's a wild ride.
It is. But before we get too far ahead of ourselves, let's rewind a bit. What were mathematicians even thinking about at the beginning of the 20th century?
Yeah.
Like, what were the big questions back then?
That's a great question. We need to step back in time to the dawn of the 20th century. It was a time of great change, a time when mathematicians were really questioning the foundations of their field. But that, my friend, is a story for our next segment.
Ooh, a cliffhanger. I can't wait to hear more about this mathematical origin story.
Welcome back, everyone. Before the break, we were about to time travel back to the start of the 20th century. What was the math scene like back then?
It was a really interesting time, you know? Lots of excitement, but also this need to make sure everything was rock solid, logically speaking.
So not just new discoveries, but making sure the old stuff was actually, like, built on solid ground. Exactly. Rigor, axiomatization, all that. Mathematicians were like, wait, are we really sure about this? questioning assumptions, trying to build everything from the ground up.
So who is leading this back to basics movement?
One of the big names was David Hilbert, like a total rock star of 20th century math.
Okay.
Yeah, and at this big math conference in 1900, he lays out this list of 23 unsolved problems.
The Hilbert problems. I've heard of those. They're like legendary, right?
They are. It was like a challenge to the entire math world. Go solve these if you think you're so smart.
So even though everyone was focused on like making math more rigorous, it wasn't about stifling creativity.
No, not at all. It was more like setting the stage, creating this fertile ground for new discoveries to happen.
And they did happen, right? In all sorts of areas.
Oh, yeah, big time. Like in analysis, for example, there was this growing focus on functions of real and complex variables, led to some powerful tools like measure theory, Lebesgue integration.
Oh, yeah, those are pretty hardcore. I remember those from my analysis classes.
They are. But they let you deal with infinity and limits in a whole new way, like a major upgrade to the toolbox of analysis.
Cool. What about algebra? Anything exciting happening there?
For sure. People started getting really into these abstract algebraic structures like groups, rings, fields, shifting away from specific numbers and equations and more towards the underlying patterns.
So instead of just working with examples, they were looking for the universal rules.
Exactly. And that's how we got abstract algebra, a whole new field that changed how we think about algebraic concepts.
So both analysis and algebra were getting more abstract. Was that just a coincidence?
Not really. It was all part of this bigger movement, trying to find the fundamental structures that connect everything in math, like revealing this hidden unity.
I like that. A hidden unity in math.
Yeah.
So the early 20th century, it was about building foundations, exploring new stuff, and finding those connections.
You got it. And one of the fields that really embodies that spirit is topology.
Topology, right. The one where a coffee cup and a donut are the same thing.
That's the one. Rubber sheet geometry, they call it. It's about those properties that don't change, even when you stretch or twist things.
Always messes with my mind, that one.
It is pretty wild. But it lets us see these connections between shapes that you wouldn't normally think are related at all.
Okay, so how did topology even become a thing?
Well, it kind of started in the 19th century, but it really took off in the 20th. Poincaré, the guy we mentioned earlier, he's considered the father of modern topology.
Right. Poincaré. What did he do exactly?
He introduced all these crazy concepts like homology, the fundamental group, basically tools to study the holes and loops in spaces.
Homology, we talked about that before, right? How it's used in so many different areas.
Yeah, and it all started in topology. It just goes to show how these abstract ideas can end up being super useful.
I'm sensing a theme here. So, topology, what other cool applications does it have?
Oh, tons. Data analysis, computer graphics, knot theory, string theory, even material science.
Wow, topology is everywhere.
It is. But, thinking about these higher dimensional spaces, those weird deformations, it can get pretty tough to visualize.
Yeah, I was just thinking that. Like, how do mathematicians even wrap their heads around those things?
It's a challenge. To be honest, visualizing stuff beyond 3 dimensions is almost impossible. So you got to rely on other tools. That's where algebraic topology comes in.
So using the power of algebra to understand the weirdness of topology.
Exactly. And that's led to some really amazing results.
This has been an incredible journey, really. We've covered so much ground, from the foundations of math to all these mind-blowing concepts like noncommutativity, nonlinearity, topology.
It's been quite the whirlwind tour, and we've only scratched the surface.
It's clear that the 20th century was a game changer for math. I can't wait to see what happens next.
Me too. And for all the math students out there, just remember, math is all about exploring, discovering new things. Don't be afraid to ask questions, push the boundaries. Who knows? Maybe you'll be the one to make the next big breakthrough.
Great advice. Thanks for joining us on this deep dive into 20th century math.
It was a blast.